In the last class, we learned a formula that works for finding the integral for simple functions. And while this is nice and easy, in fact, I oftentimes refer to this as the formula as the simple integration formula, there are more complex functions that we come across. And today, in today's lesson, we're going to learn a method of integration by substitution. It's often referred to as U substitution because we're going to use the letter U, and it's become known almost worldwide as U substitution. It's also used in different levels of calculus as well. And this U substitution works with more complex functions. The book chapter just calls it integration by substitution, but it's the same thing. Now, if you remember the chain rule, and we said when we had two equations, for example here, we have y equals to 14x squared and so on, and a second equation that uses the x, and it's equal to something in terms of t's. We said that when we take the derivative of this, using the chain rule, we would take the derivative of y and multiply it by the derivative of x. Well, that was simple enough. As part of that, I had said that what we're really doing is the derivative of y with respect to t. Our answer ends up being in t's, but it's the derivative of both of these multiplied together. The derivative dy over dt equals the derivative of y with respect to x times the derivative of x with respect to t. And I mentioned that these values, these symbols also carry algebraic values, and that it's like the dx's cancel each other out to get dy over dt. Well, just the same thing as if you do it in regular math, you can cancel out the 42s here just to get the 71 over 5. Well, that's the concept of what we're going to be doing today. It's slightly different than that. But remember that these values, even though we think of them as the derivative of y with respect to t, they also have an algebraic value. Now, with U substitution, we come in and we look at this function and say, oh, we're going to find the integral of x minus 5, the quantity squared, dx. Well, we know we can multiply it out since it's simply x, the parenthesis, everything inside the parenthesis is just raised to the power of 2, and then take the derivative of it. But there's an easier way. Now, this is a very simple example. Again, the functions can get more and more difficult. What we're going to do is to come in and do a substitution. We're going to, when we look at this particular function, we want to define the integral of, say, u squared instead of x minus 5, the quantity squared. Well, that we could do with the simple integration formula. So that's the concept behind it. We're going to substitute in u for something in this equation. Now, you'll notice that it's asking you to find the integral of this with respect to x. And if we convert this to u's, it's no longer with respect to x, it's with respect to u. So what we end up needing to do is find a substitute here for u, that we get u squared, and then find a substitute of dx that's in terms of u also. And for that, we're going to find the relationship between the two. Then when we're done taking the integral of something that we can use with the simple integration formula, then we're going to convert it back to x's because, again, our answer is supposed to be in terms of x here, dx, and not in terms of u. Now, it's not so hard as it sounds, so let's just step through a problem here. To use U substitution, there's just a few things that you need to remember to do. And basically, these are just steps to memorize or just to learn, to get familiar with. What we're going to do is to do the U substitution. So, if that's the case, we're going to do U substitution. And if we're doing U substitution, we would say, let U equal x minus 5. If I could replace the x minus 5 with u, then I end up getting the integral of u squared. And that I can use our simple integration formula for. So if I was going to build this, I'd say, okay, I'm going to let u equal x minus 5. Well, in that case, then, I would say that this is equal to the integral if u is equal to x minus 5, that becomes u squared. On the top here in the green, I'm going to be putting what the equation is equal to, what the function is equal to in terms of u. If we define u to be x minus 5, then the first part we're going to substitute here is the integral of x minus 5 squared. We're going to substitute in with that the integral of u squared. Now we still need to deal with this dx. We can't just simply go over there and write dx down because we need to keep it all in terms of 1. And the second one, where we have the integral of u squared, it has to end up being du with respect to u, since we're now doing the integral with u. So what we can do for this is find out what dx is equal to in terms of u. Now, to do this, this is just simply something to remember, to memorize. If we take the derivative of u prime is going to be equal to something. Well, one of the things we can do is use the Leibniz notation, the other notation. The derivative of u is equal to, so here, the derivative of u with respect to x. These are the same things. Now, if we actually take the derivative of u, well, we look here and say the u is x minus 5. The derivative of x minus 5 is simply 1. So it's nice and simple. Now, what happens here is we look at du and dx as having algebraic values. So what I can actually do then is multiply both sides by dx. And when I do that, then I end up saying, well, the dx will cancel off, and I get du is equal to 1 dx. And we don't really need to write the 1. We simply could say that du is equal to dx. In this case, du and dx are equal to each other. They have a one-to-one relationship. That will happen in this problem and the next one that I do, but it will not happen all of the time. If it did, we could just simply say, well, dx is always equal to du. So we would put that after the integral of u squared, but it won't always be the case. So you always have to check this. You always have to go through these steps. In this case, we wanted to substitute dx with something in terms of u. Well, here, dx is equal to du, so it's a one-to-one relationship. We can simply substitute in du for dx because they are equal to each other. So in rewriting it then, I take this up here and say that it's du is equal to dx, so I can substitute it with du. Now, I can do the integral with this, right? It's easy. We're going to be working with u to the second power, and we want to integrate this. So that's going to become 1 over 2 plus 1. Oh, it's written a little bit funny there, excuse me. Get the eraser to work. 2 plus 1. U to the 2 plus 1. And of course, it's going to be plus c. But as long as that's on the last step, that's good. So this becomes 1/3 u to the third plus c. Now again, in the original problem, we were asked to solve this in terms of u. That's what, or excuse me, in terms of x, which is what this is asking for. So we need, the last step is to substitute back in what u to the third is equal to. Well, if u to the third, excuse me, the u to the third, we can keep the third power there. We know what u is equal to. We defined it right here. So we now just simply substitute back in the x minus 5 in place of u, and we get 1/3 x minus 5 to the third plus c. So in using u substitution, basically what we're doing is breaking it down, and we're substituting in two different things. The one we did here, we substituted x minus 5 for u, and then we did what was remaining in the integral and did a substitution for that as well. Now, real quick here, I'm going to run through this again. I have it on PowerPoint, so you can actually see it outside of the video if you want to run through the example that's on Moodle. Again, we did u substitution, and we set let u equal x minus 5. Then because of that, we know that so far we've substituted in the integral of u squared for the integral of x minus 5, the quantity squared. Now we need to substitute in something for dx. So the process is find the derivative of u. So if u is x minus 5, the derivative of u with respect to x is equal to 1. Using the Leibniz notation is helpful. Then we said, well, I can multiply both sides by dx, and that cancels out the dx on the one side, and we get du is equal to 1 dx. Now, some of you will say, well, yeah, this is a helpful step in between, but we're always going to be doing this. If I do 20 problems, I'm going to do it 20 times. Won't it always end up being that du equals, in this case, 1 dx? So you could jump directly from the first, let u is equal to x minus 5, directly to this step if you remember that the in-between part, this is what we're actually doing. For some of you more comfortable with math, you can just look at it saying the derivative of u is equal to 1 dx. Some students say, well, I just write down du equals, take the derivative of this and write dx afterwards. That's fine. It's done often enough that everyone will understand what you're actually doing before that is this. But this works sometimes, especially when it's new, it's helpful to do to remember what we're doing. And if you're a little uncertain on what you're doing, writing out each step sometimes is very helpful. So, but it's up to you. You can jump directly to this step, but again, in this problem, in the first one, and in the next one, we end up with a one-to-one relationship, but it always won't be that way, so we still need to do this. Now, of course, that means that du is equal to dx. Now we found we wanted to substitute dx with something with u's in, and dx equals du, so we can simply substitute in du for dx in the equation. Now we use our simple integration formula, and we get 1/3 u to the third. Again, this is supposed to be in terms of x. So this is in terms of u, so we need to convert the u to x. Fortunately, we have that right here from what we did initially. If u is equal to x minus 5, then we simply substitute in x minus 5 for u. And remember to put on the plus c, and we're done. Now, this next problem is just a step more complex. What's happening here, you'll notice, is that it's the integral of 2x, which is one function, times another function. Well, if we look at this, I'm going to point this out because it's helpful for a future lesson. Whenever we can use substitution whenever we look at the derivative of just what is inside the parenthesis. If the derivative of what's inside the parenthesis is equal to the other function that you're multiplying, then we know use substitution will work. In this case, the derivative of x squared plus 1 is 2x, so we know that it will work. We'll also see shortly that it also works even if it's part of the derivative, but that'll make more sense in just a minute. Right now we know that the derivative of x squared plus 1 is 2x, so we can use substitution with this. Now, we still do the substitution in 2 steps, so what is helpful when we do this is to rewrite the equation, putting the 2x and the dx together. So we get the integral followed by something inside the parenthesis raised to a power, and we'll substitute first. And then the second substitution, we want to substitute for everything else that remains in the integrand. So that'll make sense in just a bit. So we go through our u substitution. Again, we let u equal everything that's inside the parenthesis, but again, no power, just everything that's inside the parenthesis. And then we find the derivative. The first step, we can write the substitution, the integral of u to the third. And now to find what we want to replace 2x dx with, everything else, we take the derivative of u. So the derivative of u with respect to x is 2x. And we multiply both sides by dx. On the left side here, it cancels out. And over here, we just multiply them together, we get du equals 2x dx. Well, that worked out really nice because here, that's exactly what we're looking for. We want to replace 2x dx with something in terms of u, and 2x dx is equal to du. So that works very well. In this case, the 2x dx and du are in a one-to-one relationship. So we can simply substitute in du for the 2x dx. Now we can use our simple integration formula, and we get 1/4 u to the 4th plus c. Now, again, everything has to be in terms of x, so we substitute back in what u is equal to, namely the x squared plus 1, and we get our final answer of 1/4 times the quantity x squared plus 1 to the 4th power plus c. So hopefully this is beginning to feel a little bit comfortable, a little bit more comfortable, I should say. It's still a little strange because I know it's a lot of steps, but we'll go through a couple more examples, and of course we have class time to work on problems from the homework. Now, a third example in using u substitution. Here we have the integral of x squared plus 2x plus 3 all raised to the 6th power times the quantity x plus 1 dx. Now, earlier I had said about if we take the derivative of what is inside of the parenthesis, in this case, that would be 2x plus 2. Well, that's not what's here. But 2x plus 2, we realized we could factor a 2 out of that to get x plus 1. So that's what I mean by saying u substitution will work if you take the derivative of whatever is inside the parenthesis, and if it's the same as this, or if this is a part of the derivative, just the same as x plus 1 is a part of 2x plus 2. We can factor the 2 out to get the x plus 1. So then we can use substitution. So in this case, that's what we want to do. We have everything in the correct order. The integral, everything inside the parenthesis that's raised to a power, times everything else that remains in the integral. It's all together. So we're going to do u substitution. We let u equal everything inside the parenthesis. So then we can say that it's the integral of u to the 6th. And now we need to substitute x plus 1 dx, or x plus 1 times dx, with something in terms of u. To do that, we always take the derivative. So du over dx, the derivative of u with respect to x is 2x plus 2. Now, when we multiply both sides by dx, we get du equals the quantity 2x plus 2, quantity closed, times dx. Well, again, we're looking for x plus 1, not for 2x plus 2. But we can get x plus 1, that's what our goal is, by factoring out the 2. So we factor out the 2, we get du equals 2 times the quantity x plus 1 dx. Well, now, this looks familiar, but we want to find what x plus 1 times dx is equal to. And it's not equal to du, because du is equal to twice that. So what we need to do is to divide both sides by 2. Whatever you do to one side, you have to do to the other side in an equation. So when we divide by 2, of course the 2's will cancel out, and we're left with x plus 1 dx, which is what we're looking for, what we need to substitute up here. And that equals du over 2, or 1/2 du. It's the same thing. I usually convert it to the fraction like this because it makes it easier once we put it up here. So we replace x plus 1 times dx, which is this, with whatever this is equal to. It's not always a one-to-one relationship, so we have to do these steps to find, in this case, that it's 1/2 of du is the relationship. So what we do is we move the 1/2 du up here in place of this. So now we get the integral of u to the 6th times 1/2 du. Now we remember that we're used to seeing it a little bit differently, but we can simply move the 1/2 out here because it's a constant. 1/2 is a number, and any time a number appears in here, you can put it over here, as long as it's not inside a parenthesis raised to a power, of course. So to see that a little bit more clearly, I put it over here because we're used to seeing it in front of when we've done the homework before. Now this 1/2 can simply come out. You don't have to do this in between step. It's just something that can be helpful for some students. So the 1/2 moves outside of the integral sign, and now we're doing 1/2 the integral of u to the 6th du. Can we do that? Sure. the simple integration formula. That's going to be 1/2 times 1/7 u to the 7th. Now we substitute back in what u is equal to, namely this x squared plus 2x plus 3. And, oops, I guess first we're going to multiply it out and then do the substitution. Usually in the homework I do both of these together, but just to separate out so it's a little bit clearer. 1/14 times x squared plus 2x plus 3 to the 7th. Here we have something that looks really not so nice, right? Well, we remember that we need to get it in all of the x's inside the parenthesis, and if it's divided by some x in some form, we know that we can flip it over and get a negative exponent. So that's what we need to do. We need to separate these. We can separate it by separating the numerator and the denominator. You can think of x as x over 1, which I didn't write the 1, times 1 over this. Well, of course, this 3x squared plus 4, and you take the square root of it, and you take the square root of it, it's the same as the 1/2 power. So this becomes the integral of x times 1 over all of this to the 1/2 power dx. And then, of course, we can flip the second one over to get the integral of x times the quantity 3x squared plus 4 to the minus 1/2 power dx. Now, of course, we said that it's easiest to see if we put what's inside the parenthesis to the exponential power first and everything else last, so let's go ahead and do that. That just makes it a little bit clearer, a little bit easier to see that what we're going to work with now is the integral of 3x squared plus 4 to the 1/2 power times x dx. So I'm just going to move this up to save a little bit of space, and now we can do the integral of this. We know that the derivative of 3x squared is going to be 6x. Well, this is in 6x, but it is part of 6x. X is a part of this, so we can use u substitution. So what we do is we let u equal everything inside the parenthesis, again, not with the exponent, just what's inside the parenthesis. So that lets us begin our substitution, that it's going to be the integral of u to the 1/2. Now we need to replace the x dx. Well, in this case, we take the derivative, as we always do. The derivative of u with respect to x is 6x, and we multiply both sides by dx to get du equals 6x dx. Now, once we've done this, we realize, again, we want to replace x dx, not 6x dx. So what we can do is divide by 6 on both sides. Whatever you do to one side in the equation, you have to do to the other. 6x divided by 6 is x dx. du divided by 6 is, of course, du divided by 6. Usually writing it in this form, 1/6 du is more helpful because we'll put this up here. Now we have, again, a number inside the integrand. And so we can move that outside. It becomes 1/6 the integral of u to the minus 1/2 du. Now can we do this? Of course we can. Simple integration formula. We would plug in our r of minus 1/2, and we work through the math. And we remember here again, we have 1 over 1/2, so we just flip this over. So it becomes 1/6 times 2, u to the 1/2. And then we can multiply that out to get 2/6, which of course we know is 1/3. And also substitute in the u. U is equal to 3x squared plus 4. Put that back in here. Remember to write the 1/2 power. Sometimes on exams, students forget that little step. Once they rewrite it, they put in what u is equal to and forget the power. Be careful with that. And of course, remember the plus c on the end. So once you do this a couple times, it usually starts coming a little bit faster. If you have any questions on the homework, of course, bring it to class. If you want to try a few before you come, you're welcome to, but you can start it in class and make sure you're on track. We're going to jump up to chapter 9 with this. And yeah, this homework, of course, is also on Moodle. So have a good day. We'll see you in class.